Hello and welcome back to IPv4 and IPv6 subnetting 0 to hero. This video is VLSM. So here's a quick review of where we are in the course. And here we are. Now here it says FLSM and VLSM, but I just said this video is VLSM. Well, in fact, everything we've been doing up to now in this IPv4 subnetting section has been FLSM. In this video, I'll introduce something a little more challenging called VLSM. Now let me explain those two terms, FLSM and VLSM. So FLSM stands for Fixed Length Subnet Masks. It is the process of dividing an address block into subnets of equal size, and therefore all of the subnets have the same prefix length. Thus the title, Fixed Length Subnet Masks. An example is dividing 192.168.1.0/24 into 8 subnets with /27 prefix length. So each of those 8 subnets is the same size. They all have the same prefix length. And as I mentioned, up to this point in the course, we have been doing FLSM only. When you're starting to study subnetting, you should start with FLSM because it's a little simpler. But now you should be comfortable with splitting address blocks into subnets of equal sizes. So let's move on to VLSM. VLSM stands for Variable Length Subnet Masks. It is the process of dividing an address block into subnets of varying sizes. Now, why do we want to do this? Well, it's more efficient because the number of addresses required in a subnet can vary. Some subnets have lots of hosts. They need lots of host addresses. So you need a shorter prefix length, which allows for more host addresses. But some subnets are smaller. Maybe you only need 5 or 10 devices. In that case, it's very inefficient to use the same prefix length for every subnet, because in those smaller subnets, which only require a few addresses, you'll have lots of wasted, unused addresses, so that's inefficient. Now, VLSM is more complicated than FLSM, but if you follow the correct process, it will only take a little practice to master it. So I think by the end of this video, you should feel comfortable with it. But then also in the next video, I'll give you some recommendations for further practice so you can continue to improve your subnetting skills with both FLSM and VLSM. Okay, so this is the process of VLSM. It's actually quite simple. First, assign the largest subnet at the start of the address space. Then, assign the second largest subnet after it, and repeat the process until all subnets have been assigned. So, for example, let's say you have a subnet that requires 100 host addresses, and then you have a subnet that requires 50 host addresses, and you have a subnet that requires 10 host addresses. Well, you would assign them in that order. At the start of the address space, the first addresses, you would assign the large subnet. And then after that, the second largest that requires 50 hosts, and then finally, you would assign the third subnet, which only requires 10 hosts. And that's how you do it. And the process is the same no matter how many subnets you need, how big the subnets are, the process is the same. Start at the largest subnet, then the next largest, and continue like that. Okay, so let's get right into an example. There will be 3 examples in this video. This first one will really go through step by step to get you comfortable. So we have an address block, a network, 172.20.0.0/24, and we have to subnet it for these 5 LANs. Actually, 5 LANs plus 1 point-to-point connection. So you need 2 addresses here for these 2 routers. Okay, so the LANs we have are Tokyo LAN A, which requires 110 hosts, Tokyo LAN B requires 27 hosts, Toronto LAN A only requires 5 hosts, Toronto LAN B 12 hosts, and Toronto LAN C 62 hosts. Okay, so these could be different departments or offices in these different cities. And also don't forget the point-to-point connection, of course. You have to assign addresses to the routers for these. So how can we do this process? Well, let's review. First, assign the largest subnet at the start of the address space. Okay, so which of those subnets was the largest? Which one required the most hosts? That is Tokyo LAN A. Notice I put the 1 here. That's the one we're going to do first. Okay, so how can we assign this subnet? Well, we should start at the beginning of the address space. So we know the address, the network address will be 172.20.0.0. That is the network address of Tokyo LAN A. Now the next question is, what should the prefix length be? What prefix length will allow us to have at least 110 hosts? Okay, so the question is, how many host bits do we need? One host bit would give us 2 hosts. Actually, not really, because you have to subtract 2, so 0 hosts. 2 host bits gives us 4 minus 2 is 2. So 4, 8, 16, 32, 64, 128 minus 2 is 126. So if you have 7, I don't know if you can see that in the camera, 7 host bits will give us 126 usable addresses. So 7 host bits from a /24 would mean a /25 prefix length, right? So the network portion will be 25 bits. The host portion will be 7 bits. So there we go. That's the prefix length. And now that you know this, you can calculate this other stuff easily. Well, I already told you the number of usable host addresses. That's 126, right? Because we have 7 host bits. 2 to the power of 7 is 128, minus 2 for the network and broadcast addresses, so 126 usable host addresses. What is the broadcast address? That is the last address in the subnet. That will be 172.20.0.127. Okay, and then the first address, the first usable address will be .1, last usable address, .126, like that. Now my writing's a little messy, so here are the answers once again. So the prefix length is /25. You can also write it in dotted decimal, 255.255.255.128. The network address, 172.20.0.0. Broadcast address is .127. The first usable is .1. Last usable, .126. And the total number of usable host addresses is 126. Okay, so that is enough because we only need 110 for Tokyo LAN A. Okay, so let's review. We just did this. We assigned the largest subnet at the start of the address space. So let's check down here. The original 172.20.0.0/24 address block contains these addresses from .0 to .255. So that's 256 addresses in total. 0 to 255 is 256 addresses in total. Then we assigned this range of addresses, 172.20.0.0 to .127. In other words, the subnet 172.20.0.0/25 to Tokyo LAN A. So that subnet, that LAN, has been assigned. Now the remaining addresses are from .128 to .255. And we will use this remaining address space to make the other subnets. Now the network address of the next subnet will be .128, right? Because it's the next address immediately after Tokyo LAN A. Tokyo LAN A's broadcast address was .127, so the network address of the next subnet will be .128. But we still have to figure out the prefix length and other things like that. So let's continue. The next largest subnet is Toronto LAN C here. It's number 2. So I just said that the network address will be .128 because it's the next address after Tokyo LAN A's broadcast address of .127. Now, what should the prefix length be? Okay, so Toronto LAN C requires 62 hosts. Okay, so let's try again. Count the binary. 2, 4, 8, 16, 32, 64 with 6 bits, minus 2 gives us 62 hosts, which is just right, actually. So if we have 6 host bits, we can make 62 host addresses, which is perfect. So starting with a /24, if we make sure we have 6 host bits, that means the prefix length will be /26, right? 26 bits for the network portion, 6 bits for the host portion. All right, and let's check the answers. There we go. As I said, the network address is .128. Here is the broadcast address. So all of those 6 host bits set to 1. Here is the first usable address, the last usable address, and the total number of usable host addresses. Okay, now I want to pause here and just say that I'm not writing all of this out in binary. In the past 3 or 4 videos, we took a look at a lot of binary, a lot of dotted decimal, and converting between them. I assume you're comfortable with that by now. Now, to solve these problems on your own, I hope you are writing it out in binary. It's absolutely essential. Until you're able to do it in your head, you have to write out the binary to really understand subnetting. So please do that. Okay, so that's Toronto LAN C, /26 prefix length, and the network address is .128. So here's that same summary again. I just added this part here. So we assigned the .128 to .191 range. The subnet is 172.20.0.128/26 to Toronto LAN C. So this is the remaining address space, .192 to .255. And the network address of the next subnet will be that 192.192, because it is the next address after Toronto LAN C's broadcast address. So the next subnet, the next largest one, is Tokyo LAN B. That is number 3. So the network address we know is .192, the address immediately after Toronto LAN C's broadcast address. Now, what should the prefix length be? So we need 27 hosts this time. So let's calculate. 1 host bit gives us 2, 4, 8, 16, 32 minus 2 is 30. Okay, so that is perfect. We need 27, and we'll have 30 with 5 host bits. So that means the prefix length will be /27. So the network portion, 27 bits, the host portion, 5 bits. Okay, and calculate these other things on your own. I hope you're doing that, by the way, pausing the video to calculate. Let's just see the answers now. There we go. Prefix length /27, as I said. You could also write it in dotted decimal. The network address .192, broadcast address .223, first usable and last usable address, and the total number of host addresses, which is enough for our 27 here in Tokyo LAN B. Okay, here's that summary one more time. This time we assigned the .192 to .223 range to Tokyo LAN B. This is the subnet address, 172.20.0.192/27. Okay, so the remaining addresses are .224 to .255. And of course, once again, the network address of the next subnet will be that .224, because, I'm repeating myself, but it is the next address after Tokyo LAN B's broadcast address. So it's the next available address. Okay, so the next LAN, the next subnet will be Toronto LAN B, and it requires 12 hosts, okay? And I just said the network address will be this one here, .224, the address after Tokyo LAN B's broadcast address. What should the prefix length be? We need 12 hosts, so 2, 4, 8, 16 minus 2 gives us 14 usable addresses if we have 4 host bits. So 4 host bits means a /28 prefix length, right? 28 bits for the network portion, 4 bits for the host portion. So let's check all of these. There we go. As I said, /28. Here it is written as a dotted decimal subnet mask. Network address of .224, like I said. The broadcast address, the last address in that range, is .239. And here we have the first usable and the last usable addresses, and the total number of usable host addresses, 14, like I said. Okay, so that is Toronto LAN B. Let's review that again. So we assigned the .224 to .239 range, that is 172.20.0.224/28, to Toronto LAN B. Now the remaining addresses are .240 to .255, and we still have 2 more subnets to assign. And the network address of the next subnet will be .240. So what is the next one? It is Toronto LAN A, only requiring 5 hosts. So we know the network address is .240. What should the prefix length be to allow us to have 5 host addresses? 2, 4, 8 minus 2 gives us 6. So if we have 3 host bits, we have 6 host addresses. So that is perfect. So 3 host bits means a /29 prefix length, right? 29 bits for the network portion, 3 bits for the host portion. Okay, so hopefully you can calculate these other things here. Let's check the answer. There we go. Prefix length /29, there it is in dotted decimal. Network address, broadcast address, the last address in that range is .247. First and last usable, and like I said, the total number of usable host addresses is 6. Okay, that's Toronto LAN A. We have one more to assign, but let's do a quick review again. So we just assigned the .240 to .247 range, that is the 172.20.0.240/29 subnet to Toronto LAN A. Now the remaining addresses, only a few left, are .248 to .255, and the network address of the next subnet will be .248. And that final remaining subnet is this point-to-point connection between the 2 routers. So we need 2 host addresses here. We know the network address will be .248. What should the prefix length be? Now there are actually 2 choices here that allow us to have 2 addresses. We could use /30, which is kind of the traditional path, still leaving room for that network address and broadcast address. But another option is the /31 for this point-to-point connection. That is an option. But it's generally recommended to do /30, so that's what I'll do here, /30. The network address, .248, broadcast, .251, first and last usable. So for example, we could assign this router here, .249, and this router here, .250, something like that. Okay, and here is the final review. So we just assigned the .248 to .251 range. That's the 172.20.0.248/30 subnet to the point-to-point connection. Now we do have a few remaining addresses. These can go unused for now. Maybe we'll need them later. We can assign them to another subnet, another point-to-point connection, for example. But for now, they are unused. But that's not so bad. Okay, so here is a summary of VLSM example 1. So we started with a /24 address block, a /24 network, and we divided it into 6 subnets, each with a different prefix length. So this one has a /25, /26, /27, /28, /29, and /30. This is VLSM, variable length subnet masks. Okay, so let's go right into VLSM example 2. I want you to do this on your own. It can take some time. You have to do a lot of calculations, a lot of writing the binary, but watching someone do subnetting isn't going to help you learn subnetting. It's not going to help you master subnetting. You have to do it on your own. So I highly recommend pausing the video now, following this same process. Start with the largest subnet, then the second largest, and then repeat until they've all been assigned. Okay, so for example, this one's the largest subnet, then this one, then this one, then this one, then this one, then the point-to-point connection. So simply assign those subnets in order. And the address space you have is 192.168.0.0/23. So you're starting with a /23 address block. Okay, here are the answers. So the largest subnet, LA LAN A, we assigned as 192.168.0.0/25. So this chart gives an explanation of that. We needed 117 hosts. The /25 prefix length gives us 126, so that's enough. That leaves 9 hosts unused, but that's fine. The network address is 192.168.0.0. This is the slash notation of the prefix length, also written in dotted decimal as a subnet mask. And here is the usable range, from .1 to .126. That's the broadcast address. And this column here, wildcard, refers to the wildcard mask. This isn't really something you have to know for subnetting. On a Cisco device, if you're configuring something like access lists, you have to know wildcard masks, but you don't have to know it for subnetting. To give a brief explanation, it's an inversion of the subnet mask. So the /25 subnet mask is 255.255.255.128. The wildcard mask is 0.0.0.127. So you just invert the bits. If a bit is 1 in the subnet mask, it's 0 in the wildcard mask. If a bit is 0 in the subnet mask, it's 1 in the wildcard mask. That's how you get this 0.0.0.127. But you don't have to know this for subnetting, really. So you can ignore this last column. Okay, so that was Tokyo LAN A. The next largest subnet after that was Boston LAN B. Or sorry, no, not Boston LAN B, Boston LAN A with 99 hosts. Okay, so we needed 99. We again had to use a /25 prefix length, which gives us 126. So even though it needs less addresses than LA LAN A, which needed 117, Boston LAN A needs 99, we had to use the same /25 prefix length. So that means there are a few more unused host addresses here, but that's unavoidable. Okay, the network address is .128. That's the prefix length, again /25, usable range. The broadcast address is .255, and again, wildcard mask you can ignore. Okay, the next largest one after that was LA LAN B. Okay, we needed 57 hosts, and we used a /25 prefix length, which gives us 62. Perfect. So that's the network address, 192.168.1.0/26. Okay, this is the usable range, .1 to .62, the broadcast address. Okay. And you can look at the rest of the chart yourself here. Okay, now if you got the answers incorrect, go back and watch how I did the first example and follow the exact same steps, step by step. And I have to emphasize again, make sure you're writing out the binary and, you understand the binary and can convert between it and dotted decimal. That's the only way to really master and understand subnetting, which is why I've said it so many times. You're probably getting sick of it by now. Okay, last example, VLSM example 3. This time we're starting with the 10.0.0.0/22 network, or address block, address range. So again, 6 subnets, 5 LANs, and a point-to-point connection. And follow this exact same process. Start with the largest subnet, the largest LAN, which is London LAN A, and then proceed down all the way to the point-to-point connection, which only requires 2 addresses. Okay, hopefully you did that. Here are the answers. So you can see here the network address of each subnet and the prefix length. So we started with 3 /24s in a row. London LAN A, 10.0.0.0/24, and then Paris LAN A, 10.0.1.0/24, and then Paris LAN B with 10.0.2.0/24. So 3 /24 subnets in a row. And then for London LAN B, 10.0.3.0/25. We don't need the full /24 for London LAN B. Paris LAN C required 54 hosts, so we assigned it as 10.0.3.128/26. And then finally the point-to-point connection, once again using a /30 to get 2 usable host addresses. So the subnet address is 10.0.3.192/30. Okay, so once again, this is how to do VLSM. Assign the largest subnet at the start of the address space, then assign the second largest subnet after it, and then repeat the process until all subnets have been assigned. That's how you do VLSM. Okay, and that's all for this video. Like I said, VLSM is a bit more complicated than FLSM. The subnets aren't all equal size, so you have to really think about, for each subnet, what prefix length do I have to use? How many host bits do I need to provide enough addresses? But if you follow it step by step, it's really not that difficult. And like I said, in the next video, I'll give some recommendations for more practice. So if you still don't feel quite comfortable, I recommend doing some more practice with VLSM, and you should learn it well. Okay, thanks for watching. See you in the next video.